Brace yourselves, this is going to be like 5 minutes of total nerd garble, but I've made some huge headway on that driver. Alright, first things first, I learned about RS-232 in the meantime. Its low is negative 12 volts and its high is positive 12 volts. That's a huge 24 volt AC swing, and it's been messing up my data going into the logic analyzer. It's been causing tons of frame errors, and I didn't get real data to look at. They're just like garbled bytes. I didn't know this. That was a headache. And then I learned that this box is actually a half duplex box that utilizes flow control. Ugh, I didn't know that either. So I'm really glad that I built this little like dongle thing out, because a lot of the RS-232 to TTL, meaning negative 12, positive 12 to 0 to 5 volts, they don't include pins like these. Not usually. So I built my own and accidentally helped myself, right? But this little circuit that I put together, as I just mentioned, converts the RS-232 lows and highs, which is that huge negative 12, positive 12, to a 0 volt low, 5 volt high, which is something that this logic analyzer is happy to receive. The RTS and CTS ports that I have connected here are going straight into it. And yes, it is 24 volts, but you know, it's kind of, I'm just thinking that's a pain in the butt, and this only has 2 channels, so channel 3 and 4, they're fucked. So anyway, that doesn't really matter. It's cheap. Buy a new one if I toast it. I don't care. Haven't toasted it yet. So, check it out. Here is a wave that was recorded, well, I guess you could say logic that was recorded, including RTS and CTS logic. Really important. I found that in writing the driver, originally I was trying to mimic exactly what the device was doing. This is the original logic, right? And I was trying to get the timing of all this stuff all set up because I didn't know. And I found out that as long as I just kind of twiddle RTS now and then with no pattern at all, it seems to work fine. And if I totally ignore CTS, it also works fine. Like, CTS is clear to send. Usually you should wait for that, but it actually does not care at all. So I'm kind of breaking the protocol slightly. So I've turned off hardware flow control, and I'm just like sending RTS myself, and it works great. So anyway, this is some of the received data in case you're curious what all this is about. In UART logic, these are bytes. So F0, 00, 00, 37, 8 bits in a byte, 1, 2, 3, 4, 5, 6, 7, 8. And then there's like a start and stop bit, which is these guys here. But anyway, this takes a while to read. You know, you record a lot of this crap, and then you see this, and you're like, oh god, what is it? And you have to scroll and scroll, and you gotta compare by using graphics. Ew, gooeys. So I got a little experimental and found this to be really handy. This is the SIGROC CLI. So PulseView, which is this program, is backed by libsigroc, which the project provides PulseView, this is first party, and SIGROC CLI. 2 ways to use libsigroc, right? SIGROC CLI is just the command line version of this. And in running it this way, with these commands, I can dump binary output. So this crap here, this data, will actually get written to stdout, which is the terminal here, right? But it doesn't know how to interpret this data, and it's not ASCII, so it's just garble. Here, watch. Start this up. Garble, garble, garble. Ugly. I have no idea how to read this, and unless you're insane, you shouldn't either. So I run this through a program called XXD, and it pretties it all up real good. Here, watch. I'll come over here, and I'll turn on one of these guys. Let it capture the mouse, turn it on, right click, and oh, it's pretty, it's hex. now I can actually see what data is going back and forth here. Look at the bottom line. Isn't that neat? That's great. Okay, and what I've been doing is kind of turning these guys off and turning them on and off to kind of see like what part of the data is important, right? Like this guy, just channel 1. Look down here on the bottom right. See how it flips that bit? And yeah, it's mirrored. It's, instead of saying F7, it says F7, F7. I don't know. But it's still useful. It's a quirk. I'm over it. So anyway, that's 1. Uncheck this. Here's 2. Come down here. Check that. That's 2. 2. Come over here. Here's 3. Check that. It's 4. 4. Why is it 4? Computer science nerds will click right in. Yep, it's binary. So, right here, this is going to be 8. And you put it all together, you get F. Yeah. So, this is 0F, right? This other part of the byte, the nibble, 2 nibbles and a byte, right? Is actually not used at all. There's only zeros being sent here. And you'll see that a lot in the data as well. If we go back here, you'll see that there are lots of places where there are just lots of zeros. Here's some zeros. Here's some zeros. You know, you get the idea, some zeros. So, oh, and, you know, half a byte nibble. Here's a 0. Yeah, so, I mean, it's not the most efficient thing, but does it really matter? Besides, I'm reverse engineering it, so I don't give a fuck. So anyway, yeah, I've been turning these on and off and figuring out what these do. And I have managed to actually map all of that stuff into a Python class, and it works great. These are the default values as determined by the original software. So if I, for example, turn on this port, then all of these are turned on and the channel bump is 0, right? So all of these are turned on and the channel bump is 0. It just steals the default settings because, I mean, I figured that would be good starting grounds, right? So anyway, it's all mapped out, and I even have a little method here that returns the bytes, encoded bytes for, you know, sending this to the 128X, and it actually works. Look at that. Here's that nibble I was talking about, the ignored part. Yeah. Oh yeah. So 8 bits in a byte. Here's 8 bits, 8 bits, 8 bits. These are all Booleans, so I'm running it through bit array. The fancy stuff, like port in and port out, which is like out 1, 2, 3, it's an integer, that gets casted right to bytes because it's useful data. It's not just true or false. And same with channel bump. Channel bump, over here I can increase it or decrease it, actually quite a lot, right? It's kind of a weird feature, but anyway, it exists, so I put it in there. And that class is being used in this other class, and this other class is initializing the 128X and sending a bunch of data and all kinds of crap. But here is a 9x9 matrix, because it's 9x9. So I'm doing a 9x9 matrix, and I'm calling a 128X patch on every one of these parts. And coming down here, I can write the port settings and call that class right here. And here's the encode method. Here's the encode method. So any one of these 81 objects I can call here. So that's a whole lot of yabber yabber yabber, isn't it? Let's actually see this thing work in action. This is the coolest part. I can't believe this actually works. So we'll go over here to the Windows 98 machine that I'm going to happily pause. which will release the lock on TTYS0. Thank you. Thank you. I'm actually going to say this. Thank you, Oracle, for doing that. I don't think Oracle did, though. I think they just bought it. So anyway, that makes me feel gross. Let's reset this, because I just kind of halted time over here. Start Scratch. We're going to start my program, run this. And the program, as of right now, just drops to an IPython shell, where you can run commands yourself, you know, these guys. Let's see some real-world stuff. This is an Ensoniq ESQ1, and it is connected to MIDI input port 3. It's a physical port on the back, right? But it's not really doing anything cool on the output. So let's connect it to something. In the same way that I would come over here and connect it here, now, because I've successfully reverse engineered it, I can map port 3, which is the ESQ1, to say port 5. So I run that, and I get a little output, which right now is meaningless to me, but it still returns it. I come over here, I press some keys. Oh my god, it's on port 5. Wow! Let's put it on port 6 too. Here's port 6. Whoa, it actually works. That's awesome. Oh yeah, watch this. It successfully deinitializes it too. So I leave the program and I'm off. So this is looking really sharp. Yeah, I mean, as of right now, it's pretty much a poor man's driver. I got some stuff I want to fix up. But from here, like, I would say I did probably 70% of the work, just kind of on a roll this evening. And I would want to wrap it in GTK, of course, but that wouldn't be too difficult. I mean, laying out this panel in GTK might take, like, I don't know, an hour. The graphics, I've never done GTK graphics before, but, you know, there's always room to learn, and I imagine that wouldn't take more than a couple days, including learning. And then you have a sweet-ass cross-platform driver to support this old thing that nobody probably uses, but I'm going to make it anyway because it'll make me happy. And I can run it, ironically, in Windows 10. That's the goal. I know it's kind of like almost demeaning, but it will be cross-platform. It uses PySerial, which happily runs on all the big operating systems, including Windows. Yeah, huge progress. Okay, it's a long video, so hey, thanks again for watching. See you later, guys.